In this lecture, we will learn about mechanisms of bioerosions. As we have learned that polymers undergo biodegradation, bioerosion, bioabsorption and bioresorption. In this particular lecture, we will learn about mostly about the bioerosion, because this is one of the very fundamental properties of a degradable polymer, that how we can utilize it in terms of as a drug delivery device, or maybe using some controlled degraded polymers for certain structural supplements, or by assisting drug delivery. So there are certain mechanisms of bioerosion that's what we will consider in this particular lecture. Also we'll learn about certain biopolymers, because we already learned about the biopolymers, what kind of polymers which are available, and how their chemical nature can really affect the degradation part. So we'll learn about the intricacies in this particular lecture about how bioerosion is responsible in terms of degrading a particular biopolymer. So first of all, coming to the bioerosion part, bioerosion is nothing but the transformation of a solid polymeric implant into certain water soluble materials. So we have a polymeric material and it is water insoluble, and through certain activity it basically becomes water soluble. So in this particular case, there are certain macroscopic changes are occurring with the bioerosion, and those can be such as swelling. So the overall appearance of the material itself is changing, so that can occur by swelling. So the overall volume of the polymeric material increases. So in this case, we have a volumetric enhancement of a particular volumetric enhancement can occur, or the material itself can deform, because once this erosion is occurring, the overall deformation of the material will occur. So in one case we started with a smaller material, the swelling will be increased in its volume. So this is, in this case it's swelling. But in case of deformation, the material shape can itself change. So this is nothing but the deformation. At the same time, there can be certain structural disintegration. If we had a particular polymeric starting material like this, then later on we can have certain structural disintegration, that the overall structure may be incorporated with certain porosities out here and there. So overall damage can occur through structural disintegration. There can also be weight loss, because once this polymer is capped into certain entity, it can be hydrolysis. So the material will start losing its weight. So initially we started with certain material, and then later on we will have some different material. It might have lost its structural integrity as well, but at the same time there is some weight loss. So we have swelling, we can have some deformation, we can have some disintegration, and we can have weight loss, and eventually all these basically lead to eventual loss of the function, because as since the functionality is dependent on the kind of material we have available, the quantity of the material we have available, the weight of the material we have available, also the chemical nature of the polymer which is available at the end of a particular cycle or the storage. So that is the reason we can have certain bioerosion can be, it can basically elicit effect macroscopically. So the overall appearance can change either by swelling, so the overall polymer can swell, it can deform, so the deformation can also occur. There can be some structural disintegration, that the overall structure can also change, and also the weight can also be reduced because of its dissolution in the particular environment, and that leads to eventual loss of function. So in this case, in case of bioerosion, we see that there is a transformation of a solid. So the polymer has to be a solid, then only it can basically get bioeroded. So it is a solid polymeric implant. It was initially water insoluble, and that after bioerosion it becomes fragmented into certain molecules or certain set of polymeric chains which become water soluble after the bioerosion, and that is imparting certain macroscopic changes. So we can easily change the appearance, the change in the appearance of a particular device, and that can occur with the bioerosion. The material can either swell or the device can swell. So swelling is nothing but the volumetric enhancement, in case it will start absorbing the water. So so the hydrolysis might cause the increase in the overall volume, so it will lead to the swelling. It can again lead to deformation, because once it is undergoing certain changes, some part might get deformed as well, depending on how the erosion is occurring. So that deformation can also be a part of that can also be a result of the bioerosion. There can be structural disintegration in terms of the dissolution of a particular polymer. It might start disintegrating. So there can be a weight loss also associated with the structural disintegration, and that lead to eventual loss of the function. So we can see that the mechanism, though we talk about the bioerosion, that it is changing the overall appearance in terms of swelling or by deformation or by disintegration or by weight loss. So there are certain mechanisms which are associated with the bioerosion, and again they result change in the physiomechanical properties. And again all these mechanisms, they are distinct and they can be even independent of each other in terms of imparting this complex bioerosion process, because it is a combination of certain entities, and as well as they can be independent of this particular bioerosion process. Again, this bioerosion is always does not mean that there is a cleavage of the polymer backbone or the cross linking or the side chains. So we have an overall backbone, there can be disintegration of the overall backbone, this is the overall backbone. It can also be because of the cross linking with the other polymer, or it can also have some certain side chains. So it might have certain side chains or the functional groups, so that can also be altered during the bioerosion process. So again, it is always not limited to such things. It can may not be always the backbone or the cross linking or the side change. It can also occur by certain change in the environment itself. So if we have certain change in the environment, that can occur because of change in the pH, and because of change in the pH, we can also have certain solubilization of the polymer, and that can lead to the erosion of the polymer. Additionally, we can also have certain other aspect. It can also be temperature, because of the human body temperature is around 37 degrees centigrade, and depending on the overall the TG or the glass transition temperature of the polymer, there can be difference in its state. So it can be either glassy or it can become much more amorphous. So depending on that, it can again have very different mechanical properties. It can also have very different chemical properties. So in terms, it will have a very different affinity for the flow or the uptake of the water, and then again it can lead to very strong hydrolysis once it is in amorphous state. So the feeble changes in the TG temperature as well can lead to the bioerosion. So we can see that mechanisms of bioerosion, they are very complicated. They can be very distinct and independent of each other, and they impart changes in the physiomechanical properties. And again, bioerosion is not limited to the chemical entity or the chemical cleavage, which can occur either in the backbone or the cross linking part or the side chains to result the deterioration of the polymer. And again, the bioerosion can also happen by changing the temperature or by changing the pH, and that can again alter the overall solubilization of the polymer. So the overall solubility of the polymer can also get altered in a particular environment, and that can again lead to the erosion of the polymer. So we can see how the complexity is associated, how complex this particular process of bioerosion is there for the biodegradable polymers out here. So again, depending on what kind of polymer is it, we can also have two kinds of erosion which can occur. One is the bulk erosion, or second can be the surface erosion. So first let us consider the bulk erosion part. So in this case, what is happening, that the rate of water penetration into the polymer is greater than the rate of polymer transformation into water soluble materials. So we have a certain rate, we have a polymer, then water starts to seep in, and the rate of water penetration is much more faster. It will go much deeper into the polymeric material by the time that this entity which is there on the surface gets solubilized in water itself. So we have rate of water penetration, so water is penetrating to a very rapid extent, and in the meantime there are some products which are forming along this regime which are getting disintegrated, or they are getting transformed to water soluble entities at a much slower rate. So what is happening, that this process of dissolution of this particular polymer into water soluble material is happening at a much slower pace. So water is seeping down to a very faster extent even in the bulk of the polymeric material. So in the process, what is happening is that uptake of water is happening first, and that is being now followed by the erosion process, and now that happens in the entire volume of the polymer, because our water penetration rate is much faster than the rate at which the material will turn into water soluble component. So before it is really exposed to water, after the surface has been dissolved, the water is already penetrated into the bulk of the material or the inner part of the material. So what is happening in the process, that as soon as water is entering, it is getting already absorbed, or the uptake has already happened. In the meantime, the surface is experiencing the conversion of polymer into water soluble components. So, what is happening? As soon as the water the material is turning into water soluble component, it leaves a certain pore, crevice or a crack. So, now that cracks and crevices, they start developing throughout the device, because of the process of water penetration is much faster and the rate of dissolution of this polymeric material into water soluble component is much slower. So, with time we start seeing cracks and crevices in throughout the device, and that leads to the rapid crumbling of the device into pieces, because as soon as we have a particular polymer and we start seeing the cracks, and this process is little slower than the water uptake, and we see rapid crumbling, because water is now seeped throughout the material, through the bulk of the material, and that is what is leading to the overall sudden failure or sudden crumbling of the device into the pieces. So, it can be also seen more like a dissolution of sugar cube. So, if you keep a sugar cube in a water, it will start crumbling rapidly or suddenly. So, again this crumbling is again uncontrolled, and that becomes a disadvantage of the bulk eroding device in certain applications, because we want the erosion to be complete in a certain controlled manner, and in this particular case bulk erosion, the overall deformation is occurring in a very uncontrolled manner. So, that is what we see, that in the bulk erosion we have water penetration which is much more faster. So, it will rapidly occupy the overall bulk or the inner part of the polymer. So, water is already seeped throughout the polymer, and in the meantime the water soluble products will start forming, and they will form randomly throughout any location. So, what is happening in the entire process, that now we start seeing some cracks, crevices and pores which are basically now being taken up by the surrounding liquid. So, in that particular case, once it has formed certain cracks and crevices, very rapid crumbling of the device can occur, and since this whole entire process is uncontrolled, that the process cannot be controlled, it is uncontrolled process, that becomes a disadvantage in certain cases, because say for example like in drug delivery, we want a very controlled degradation of the polymeric material. So, that can be now attained by when we can control this bulk erosion and we can make it much more surface sensitive. So, in case when we have only surface erosion occurring, we can somehow get over this particular disadvantage. So, now we come to the surface erosion. So, in this case what is happening in case of surface erosion, the rate of water penetration is much slower than the rate of polymer which is not transforming into the water soluble materials. So, in this particular case we have water penetration, it is occurring at a very slower rate, and in the meantime this process is so slow that by the time it goes incrementally, this surface now gets dissolved, then only water can further penetrate to the second layer, and now second stage of the dissolution basically occurs. So, it is more like this. So, this thing has already been given, like, which is this state. So, once it has dissolved, then only water can penetrate further and start attacking the surface. So, in this case what is happening, we have rate of water penetration which is occurring at a very slower pace, and that is so slow that the rate of the rate at which the polymer is degrading is much faster. So, the rate of degradation of polymer is much faster, and then only water is allowed to pass through it. So, what is happening in the process, as soon as the water is sitting on the polymeric surface, it sits there for a certain time, and in the process the polymer starts degrading. Only when the polymer has degraded, then only the next layer of the polymer gets exposed to the water which is sitting on the surface of the polymer. So, we can see a very sharp interface. We can see a very sharp interface between the polymer which had been degraded and the polymer which is now being exposed to the hydrolytic environment. So, what is happening? So, the transformation of the polymer to the water soluble material is now limited only to the surface, because the water penetration is so slow that the water penetration, it cannot go to the bulk and it can limit itself only to the surface. So, that is the advantage of this particular process, that surface erosion is now limited only to the surface, and it is specific to a particular material depending on its hydrophobicity or its chemical nature or its molecular weight, and there are certain paradigm of parameters or factors which will basically dictate that. So what is happening in the process? The divide starts becoming thinner and thinner while maintaining its structural integrity. So it is not like the previous case when the entire polymer is now being uptaken by the water and there will be sudden cracking and crevice formation in the entire of the material. In this case, on the surface starts degrading and the structure maintains its structural integrity, because it is only surface which is getting damaged first or getting absorbed. So it gets thinner and thinner because of the degradation process, of the surface degradation process, but it maintains its structural integrity. So that is the advantage of this particular surface erosion. So again, in this particular case, the polymer must be hydrophobic enough to repel water, to inhibit water intake into its bulk, or to let it go inside its inner part, the inner of the material. And again, the dissolution rate of the polymer has to be reasonably fast to allow drug release with surface erosion. So again, we need to control this particular dissolution, that has to be reasonably fast. Though it is hydrophobic in nature, the dissolution rate has to be good enough so that we can allow enough drug to be released within certain time duration. So that is what is happening in this particular case. We are allowing in the surface erosion, we have rate of water penetration which is much slower. So in the process, only the surface is getting eroded first. After surface erosion, then only the next layer of the polymer gets exposed to water, and then it starts becoming disintegrated into the water soluble components. And in the process, we can the material maintains its structural integrity, and for doing this particular kind of surface erosion, the polymer has to be much hydrophobic to inhibit any water uptake into the bulk. At the same time, the dissolution rate of the polymer has to be controlled, or it has to be reasonably fast so that the drugs can be released in a timely fashion. So that is the overall thing with the surface erosion. So how it compares with the bulk erosion. So that is what is observed here, that the SEM evaluation, it shows very sharp border at the interface, because once we have certain entity, like we have water soluble and water insoluble, so we can see a very sharp interface between the intact polymer and this is the degraded part. So that is what we can see in the surface erosion. But in the bulk erosion, what we might expect is the water is already seeped through, so we might see certain areas. So even though water uptake is only till here, like water uptake will be throughout, only certain material will be degraded here and there locally. So that is the actually problem with the bulk erosion. But in the surface erosion part, we see a very clear boundary between at the interface. And again, it is obtained only from a few polymers which are such as polyorthoesters, and which are containing certain reactive hydrolytic bonds in the backbone. And again, they can be utilized as slab like devices which can release drug which is embedded again in the polymer at a very constant rate, because in this case only surface is getting degraded. So depending on, we can easily estimate or predict what will be the degradation rate of the particular polymer. Apart from this, though we can say that we are getting a very sharp interface, only the surface is getting degraded, so we can somehow control, and we can get a constant rate of dissolution or degradation, so it can have very controlled drug delivery. But that may not be the case all the time, because there might be certain enzymatic surface erosion can also occur. So in presence of certain enzymes, they can also penetrate into the interior of the solid. So in case when enzymes are getting penetrated, they will tend to absorb some more water and they can mediate the surface erosion. Such as in case that the cross-linked polycaprolactone, though it has a high solubility and low melting point, this can occur, the enzymatic activity can occur in the cross-linked polycaprolactone. In this case, the enzyme can assist breaking of the cross-linking or the backbone, and in that particular case, it can mediate the surface erosion of this particular polymer. So that is what we can see, that the surface erosion, it has a very sharp interface, and again it can be shown only by a few polymers, so that they can have a controlled rate of degradation. But again, though they might have very controlled drug delivery, they can also be assisted by certain enzymes, and in that particular case, it can penetrate much deeper into the material, and then it can somehow lead to the surface erosion, which can happen to them at much rapid rate, or it can also occur in the bulk of the material. So chemical degradation, it can basically, it is the underlying cause of the bioerosion. Though the bioerosion can occurs by the solubilization of the polymer, the main reason behind the bioerosion is nothing but the chemical degradation, and chemical degradation is the occurrence of the cleavage. It can be either by the cleavage of cross links which is between the chains, it can also be the cleavage of the side chains which form the polar groups, or it can also be the breakage of the polymer backbone itself. And again there can be a combination of these mechanisms which might be occurring. So in this particular case we can see the combination of this mechanism can occur. First of all, there can be a breakage of the cross links, and once it has formed a particular polymeric chain, then it can lead to the cleavage of the backbone. So in this case we have mechanism 1, cross linking between the chains is getting cleaved, then we have side chains which are getting cleaved, and in the third case we can have a polymer backbone. So in this case we are seeing a combination of 1 and 3. So in this case we are seeing a mechanism, first degradation of the cross links, and then formation of the degradation, the cleavage of the polymer backbone to cause the chemical degradation. So there might be certain causes of the bioerosion, but mainly the bioerosion is, the fundamental cause of bioerosion is basically by the chemical degradation, and that degradation can be either the removal of the cross links, or it can again be the cleavage of the side chains, or it can be again the cleavage of the backbone structure of the polymer itself. So that those are the basic reasons of the chemical degradation. And again in first case we can see the cleavage of the cross link, it can also occur between the chains. So once we can see that we have a particular polymeric chain, and it might have certain cross linking with the nearby chain. So we can see this is the main chain, and it is again, it has now certain cross links. So it can have certain cross links out here. So we can see there might be certain cross links out here, and this is the overall chain, the polymeric chain. And these cross links are the basic responsible that the overall polymer becomes very water insoluble. So in this case we have water insoluble chain. And in case 1, in the mechanism, what is happening, we have initially we have water insoluble chain, and then what happens is the cleavage of the cross link starts happening. So in this particular case we are left with, so what is happening, we have now this similar polymeric chains which are now standing in isolation but without any cross links, and now the inherent nature of these chains are that they become water soluble, because there is no cross linking available out here between them. The chain gets much more freer, the cross links which is happening between the chains. So the overall polymeric chain which had a very strong cross linking with the nearby chain, those links are now being broken, and now that becomes a much more simpler chain, and that simpler chain is much more free and small, and that is nothing but water soluble. So that is what is happening in this particular case, that we are observing the overall breaking of the cross linking itself to result a water soluble molecule. So initially we started with a water insoluble molecule which had a very strong cross linking, and now that breaks down to the very simple water soluble polymeric chain. And similarly what can happen in cleavage of the side chains, what is happening is that we can have overall chain with certain side chain. It can have certain side chain, and due to non-polarity of this particular non-polarity of this particular polymeric chain, this chain is water insoluble. But in process what is happening, the cleavage of all these polar chains, of the side chains, can form something which is much more polar, or it can be much more charged. So what is happening in the process, that the overall basic chain, the backbone of the chain remains as it is, but the side groups that now become charged. So now we have polar groups which are attached out here, and that makes the chain water soluble. So initially we had water insoluble polymeric chain, and now because of the cleavage of the side groups, or maybe some formation of transformation of this side groups or the side chains into charged polar chains. So in this particular case we have A transforming to B. So the overall backbone remains the same, but the side groups they basically are cleaved, and they result a polarity or some sort of a charged region or polar, which makes it water soluble. So in this particular case, once we have a breaking of the cross linking In this particular case, we have breaking of the or the cleaving of the side chains to result water soluble polymer. So we are starting with water insoluble chain, and we have cleaving of the side chains, and that results formation of certain polarity or the polar groups, and that makes the polymer soluble in water. But there can be third mechanism as well, that there can be the cleavage of the backbone itself. So in one case, when the overall chain itself is water insoluble, it can lead, the overall breaking of the backbone itself can also occur. The cleavage can occur along this particular bond between the certain smaller polymer molecules. So in the process, what is happening, we might get certain isolated smaller soluble polymers. So initially we had water insoluble molecules. In the process, we are breaking the or cleaving the bonding in the backbone itself. The overall backbone itself is now getting cleaved. So we get small pockets of or isolated polymers, which are very small, which are very simpler molecules. So that is what is happening in this particular case to make it water soluble. So in first case, we have breakage of the cross link itself. In second case, we have cleaving of the side chain, and third case, the cleaving of backbone is occurring. And this might be the entire, or it might be the final, basically the final process which might be occurring in the chemical degradation as soon as the polymer is becoming totally water soluble or getting totally cleaved. So that is what this might be the eventual process which is basically dominating in terms of dissolving or eroding a biodegradable polymer. So that is what we can see out here. And in certain cases, the hydrolytic or enzymatic polymer degradation, in case we have hydrolytic or enzymes can also sometimes assist cleavage apart from only the water or the hydrolytic environment. Sometimes enzymes and microorganisms can also serve as an agent to cleave the particular bonding between the polymeric chain. It can also cleave either the cross links or the side group chain or also the backbone itself. And again, but again in this both the cases, it becomes possible to distinguish the hydrolytic or the enzymatic degradation, because in one case we know that in one case we have hydrolytic degradation, it can occur only on the surface, whereas enzymatic degradation can occur even in the bulk of the material. And that is possible. Why? Because availability of water is constant in all the soft tissues, but the enzymatic activity, it differs very much, not only in patients but also at the different activity sites. So depending on where we have more enzymes, it can show a very drastically different behavior, because if we have certain water in certain localized patients or cells, the overall availability of water is constant in all the soft tissues. So the soft tissue water content is almost constant, whether it differs very slightly either in patients or at different locations of the particular patient. But enzymes, their overall concentration is very different, not only in patients but also at the different sites where they are present. So again, hydrolytic cleavage, it becomes much more predictable, because now we know that the overall concentration of water in cells or in patients is almost constant. So the degradation will occur in a very controlled or predictable manner. Whereas once we have enzymatic cleavage, it becomes very unpredictable. So in this case, we have it becomes very less useful material as a degradable medical implant. So again, we can see the degradation can occur either via hydrolytic or enzymatic conditions. So this hydrolytic degradation is very predictable, because the water content is very similar either in cells or at different or even in patients, whereas the enzymatic activity differs very drastically either in cells or in different patients. So that assists us in basically delineating how the degradation is occurring, whether it is occurring either by hydrolytic or by enzymatic action. So if the material is deforming very in a predictable manner, it is because of the hydrolytic degradation, whereas if it is unpredictable, it is because of the enzymatic activity. So that part again we can clarify, we can see, or we can easily emphasize through. Again, factors which dominate which influence the bioerosion, basically or virtually all polymeric implants which degrade, they degrade by the backbone cleavage. So as I said earlier, that the backbone cleavage is the eventual consequence of all the processes, because that is what is resulting in the overall degradation of a particular polymer into water soluble components. Again, but apart from that, there are certain factors which can influence the bioerosion, and those can be chemical stability of the polymer backbone itself. So the polymer backbone itself is much more stable, it will not allow the easy degradation of the polymer. It can also be affected by the hydrophobicity. If the material is hydrophobic in nature, it won't allow much water uptake. It can also be dependent on the molecular weight. So depending on if the material has a very high molecular weight, it has much more cross linking, then obviously the overall degradation will be much more slower. Again, the presence of catalysts, additives and plasticizers. So depending on the assistance which it can get from either catalysts, additives or plasticizer, it can affect, or the overall bioerosion rate can be controlled. And again, the geometry of device, depending on how the device has been fabricated or processed, we can have very strong influence of how the particular bioerosion will occur in a particular device. So we can see that all the polymeric materials which are now being degraded by the backbone cleavage, and they can be affected by the chemical stability of the polymer backbone itself, by the hydrophobicity, even by the molecular weight, or by the presence of external additives, catalysts, agents, plasticizers, or even the geometry of the device. Let us look them one by one so we can get a better feel of it. So the backbone of polymer, in terms of deciding the biodegradability or the overall disintegration of a particular polymer, it is one of the most fundamental factors, and in certain cases it is being dictated by the chemical nature of the polymer. In some like in cases the anhydride bonds, it will hydrolyze much faster. So hydrolyzation rate of anhydride is much faster than the ester, and again ester's degradation rate is much faster than that of a amide. So we can see that anhydride bonds, they hydrolyze very rapidly. So that's what we are seeing, and thus they will degrade at a much faster rate. So polyanhydrides will degrade much faster in comparison to the esters or polyesters, and polyamide might be much more stabler, or they will degrade at much slower rate than that of a ester. So we can have a polyanhydride which can degrade in very short duration, followed by polyesters which can degrade at much slower rate, and polyamide even being slower than the polyesters. So again, the susceptibility of the polymer towards the hydrolysis is also very important. Though this is dependent on the overall chemical nature like anhydride, ester and the amide bond, there is additional factor of the hydrolysis part. How much they are susceptible to the uptake of water, and then in combination with that we will have some hydrolytic degradation, and that will be helpful in predicting the overall tendency of polymer to degrade or get bioeroded. So first of all we have the chemical nature, and then that has to be assisted by the overall hydrolysis part of it. So how the hydrolysis is occurring, what is the overall susceptibility of this particular chemical in terms of uptake of water, and then eventually leading to the degradation of the biopolymer. So again, as we see that the polymer backbone alone is not enough. We also need some other parameters, which is nothing but the hydrophobicity. So depending on how much is the overall affinity of a particular chemical to take water, to uptake water and the polymer. So again, then the hydrophobicity becomes a function of the starting monomeric unit, because the chemical nature of the material, it starts with the monomeric material. So monomeric material decides what is the overall affinity of this particular chemical towards hydrophobicity. So we can see that there is a combination of chemical as well as the hydrophobicity in terms of dictating the bioerosion. And again, in this case we can see the erosion rate of polyanhydride, it can be restricted by 3 orders of magnitude as soon as we replace the sebacic acid with the hydrophobic bis carboxyphenoxypropane. So in one case, once we have this polyanhydride, if we can replace this if we can replace the sebacic acid with much more hydrophobic monomeric unit, which is hydrophobic bis carboxyphenoxypropane, and then that one actually is making it super hydrophobic. It is making it much more hydrophobic. It can increase the super hydrophobicity by around 1000 times, or 3 orders of magnitude. So that is what is happening. That is what is the effect of hydrophobicity. And again we can see that the PGA can erode much faster than PLA, because PLA is much more hydrophobic in nature, though in both the cases we have the same ester bonds. So in both PGA as well as PLA we have same ester bonds, but though they have the same chemical reactivity, but because of hydrophobicity PGA is dissolving at much faster rate. So in this particular case we can see the overall effect of hydrophobicity, that though the polymeric backbone is one of the very key things about the polyamides, polyesters and polyanhydrides, the polyanhydrides being the fastest, but fastest degrading material. But again apart from that, the overall susceptibility of water uptake to penetrate into the polymer and then lead to hydrolysis is very different. So like in certain cases, if the overall erosion rate can be restricted by around 1000 times or the 3 orders of magnitude, just by replacing sebacic acid with much more super hydrophobic, with much more hydrophobic bis carboxyphenoxypropane in the polyanhydride, it can reduce its degradation rate. And again PGA and PLA, they have the same chemical reactivity, but because of hydrophobicity of PLA is much higher, then it can degrade at much slower rate than in comparison to that of a PGA. So that is the overall deal with the hydrophobicity. Yes, so apart from the overall backbone structure or the chemical nature of the material, apart from its hydrophobicity, morphology is also very critical in terms of dictating the bioerosion rate which is now occurring in the degradable polymers. Like in certain cases, when the polymers which have a Tg much greater than 37 degrees centigrade, they are in the glassy state, and this 37 degrees centigrade is important because that is the human body temperature. So polymers with Tg lesser than 37 degrees centigrade, they will be more in the rubbery state. So in this case, what is happening when Tg is when Tg is greater than 37 degrees centigrade, and so below this temperature material will be very hard, or it will be in glassy state, and once they have a Tg of less than 37 degrees centigrade, so heating above this particular temperature, the polymer will become very soft, so it will become more like a rubbery state. So in certain cases the polymers can be either amorphous, crystalline or semi-crystalline. So in the case of crystalline polymers are very densely packed. So once they are densely packed, it becomes highly improbable that water can get very easily into the bulk of the material. So once for the crystalline polymers, they show highest resistance to the water penetration. So there is a combination of all this. So first let us see only the crystalline polymers, that they are densely packed, so they show very high resistance to water penetration. And again, so again in semi-crystalline, what happens is there is higher hydrolysis rate only in the localized region where we see amorphous regions. So amorphous regions of the semi-crystalline polymer, they show very high hydrolysis rate. And again this particular part becomes very important, because this becomes very important for 50% crystalline PGA, because in this particular PGA we will have certain regions which are amorphous and certain regions which are crystalline. So we have certain regions which are very highly crystalline and certain regions which are highly amorphous. So the amorphous regions will now be getting targeted first. So this amorphous region, this one will start degrading first. So the overall bioerosion rate is also dependent on the overall morphology. If the polymer is much more crystalline in nature, it will resist the water penetration. If the material is semi-crystalline, obviously the polymeric, if semi-crystalline, then obviously the amorphous regime will get targeted first, and the crystalline regime will remain intact to a very larger extent in comparison to the amorphous material. So those polymers which are semi-crystalline, such as PGA, 50% crystalline PGA, that will experience some degradation mostly in the amorphous regime, and that will tend to crumble the overall structural integrity of the PGA itself. So that is what is very critical. And again the polymers, they have different glass transition temperatures. So depending on that also, the material can either remain glassy or become rubbery. So again glassy materials will have high resistance to water penetration, whereas rubbery materials, they tend to degrade much faster. So again like in case the morphology is very critical, because in case of say poly L lactic acid and poly DL lactic acid, they have identical backbone. So the overall backbone is very similar. They have identical degree of hydrophobicity as well. So obviously we will tend to expect, oh, they should degrade at the same rate. because of poly L-lactic acid, poly D-lactic acid, similar chemical nature, similar hydrophobicity, but because of the difference in crystallinity, like our stereoregular poly L-lactic acid, it is semi-crystalline in nature, whereas poly D-lactic acid is amorphous. So in this case we can see stereoregular poly L-lactic acid, it becomes much more semi-crystalline, and it has, since it has much more regimes of it has much more crystalline regimes, it basically degrades at much slower rate. So devices made of poly L-lactic acid, they will degrade at much slower rate than that of a poly D-lactic acid, because our poly D-lactic acid is amorphous in nature. So we can see in this particular example that though have chemical, they have similar or identical chemical backbone, they have identical degree of hydrophobicity, but because of the difference in the morphology or the overall structure, that one is amorphous, one is crystalline, semi-crystalline, that is leading to the change in the overall degradation of the material. So that is a very critical part of it as well. So we are concerned about the overall backbone, the overall hydrophobicity, as well about the morphology of a particular polymer in terms of dictating the degradation rate. Again, as we talked about the glassy and rubbery state, that is dependent on the glass transition temperature. So as we said earlier, the polymer which is in the glassy state, it is less permeable, whereas polymer in the rubbery state is much more permeable. So obviously when the permeability is very high, water can seep in at much faster rate. So the particular polymers which actually experience body temperature and they have Tg just above or just below the body temperature, they will be much more rubbery in nature, and in case there are certain fluctuations in temperature, or the water can basically seep through, or there are certain enzymatic activities that can lower the Tg to below 37 degrees centigrade. Even when the Tg is above 37 degrees centigrade, marginally above 37 degrees centigrade, enzymatic actions or hydrolytic actions can reduce this Tg to say below 37 degrees centigrade, and that will tend to crumble the device. So because water absorption can occur or enzymatic action can occur, and that can reduce the glass transition temperature of the polymer, and that will make it rubbery, and rubbery means more permeable, and that will lead to a strong degradation or the absorption of the polymer. So that is what is happening, that if the temperature is above the Tg, the material will become very flexible, much more permeable, and that will lead to the overall rapid degradation of the polymer out there. And apart from that, this enzymatic action or the overall nature of the morphology, processing also is very critical, because processing is the one which can dictate or change the overall structure or the morphology of the processed polymer. So in certain case, like when we have polyanhydride which has now been processed by melt encapsulation, it was very dense, so it is eroding very slowly. So we have certain melt encapsulation, so we have certain melt which has now been encapsulated, so we are getting certain device, polymeric polyanhydride. So this is the capsule, this is the envelope, and this is the overall melt. So now once we have polyanhydride which has been processed by melt encapsulation, so we have a kind of capsule over it, so that makes it very dense. So we have a dense structure, and same polyanhydride which is now made by solvent evaporation, it will result in a kind of a microsphere, but now this microsphere has many pores, internal pores out there. So we have pores, this is a kind of a microsphere. So now this one will degrade at much rapid rate. So very rapid degradation of this microsphere which has been prepared by solvent evaporation, whereas for this one the degradation rate is very slower, because this is very dense. So we have polyanhydride which is processed by the melt encapsulation, it is much more resistant to degradation, whereas by solvent evaporation it is much more prone to degradation, because it has very large number of pores and it is very loosely packed or very less dense material. So that part we can attain from the different processing route. So by altering the processing route, we can again change the overall degradation of a particular material. So the overall technological engineering, we can say that the bioerosion is not an inherent property, it is a controllable property. So that part we can very understand right now from this particular lecture. The bioerosion can be easily controlled depending on the overall backbone, the kind of enzymatic action which can be plausible, or again when they have what was the overall hydrophobicity of the material, and even when we have particular hydrophobicity, if we can alter the structure or the morphology of it, or by which we can really process the material, so it becomes a very controllable property. So we can somehow make it dependent, it is dependent on the overall chemical nature of the backbone. So if we can alter the backbone, we can again control the bioerosion. By changing the molecular weight of the polymer, we can again have much control on the bioerosion. It also depends on the additives. So kind of additives we are adding, it can plasticizer, catalyst, binders. So those can also alter the overall degradation of the polymer. Again it is dependent on the manufacturing device. Again the geometry of device can also play an important role in terms of its degradation. Like if we have certain device which is kind of a spherical in nature, so it has a very high surface area, and if we can introduce certain pores in it, so this device might degrade at a much faster rate than a kind of a slab which is highly dense. So this dense device may degrade at a much slower rate in comparison to a porous spherical entity. So there are certain technological engineering is also possible by controlling the overall chemical nature of the backbone, by controlling the molecular weight, or by controlling the additives, or even by the manufacturing process. So those are certain parameters which are available to us in terms of dictating the degradation rate which we want in a degradable polymer. But again we have certain limitations, like we want there is something called process stability, that we need the device to be stable enough for a much longer time till it has completed its task. So if the device starts degrading at much faster rate than predicted, then it has not served its purpose. So in case we want to inject a particular drug into the material, into the body, say for a duration of 1 year, and in the process the overall device is getting consumed in say 4 months. So what about the remaining 8 months? So it has not completed its task for the next 8 months, and then that next 8 months can be highly critical, and that might lead damage the overall functionality of the person or the patient itself. So in that particular case, we need to produce devices that are stable till the task is basically completed. So they should not degrade when they are supposed to store the particular drug. So again they should be resistant to moisture when they are being processed, because during processing it should not start degrading there itself when the processing is occurring, because processing is occurring at much higher temperatures. So like in injection molding or compression molding, so they should be resistant to moisture, because if there is some moisture uptake, they can start degradation. So they need to be controlled, they should be processed in controlled atmosphere, or they should be resistant to moisture during the processing. So we should keep a check either on the temperature as well as the glass transition temperature or the hydrolytic degradation when the processing is occurring, and we should do the processing in a controlled atmosphere. It should be controlled the ambient humidity as well. So in this particular case we have a controlled atmosphere, keep a check on temperature as well as the overall humidity of the chamber, so that the device should not start degrading when the processing is occurring. So we need to keep the device much stabler for a much prolonged time, so that it can complete its task what is assigned to it. And apart from that, the materials also need to be sterilized, and also they need to be stored for a certain duration before they are injected into the patient. So there can be sterilization by gamma irradiation, but this gamma irradiation can cause backbone degradation, such as some polymers such as PLA, PGA, PDS. They are highly sensitive to gamma exposure, and that leads to damage of its backbone. So in this case this sterilization may not be really good enough, but gamma sterilization can also be useful for certain other polymers. So in case of PLA, PGA and PDS, ethylene oxide treatment can also be given, but the problem with ethylene oxide is that it is highly toxic and it is basically a safety hazard. So that is again gives and takes of certain materials, that if they are prone to gamma damage, then they have to be treated with ethylene oxide. But again ethylene oxide, we have certain concerns about its safety, that it needs to be properly cleaned up because it is highly toxic and it can also become a safety hazard. And again after it has been sterilized, the material has to be kept in an airtight container which is an aluminum bag, and it is again kept in the plastic foil pouches, so to avoid the degradation part of it. And in certain cases even refrigeration may also be necessary. So for long term storage, because if you want to use the device after a certain hold period, the material, the overall device needs to be sterile, to be kept under refrigeration, so that it should not degrade with time. So we can see there are certain aspects which are related to either the processing or the sterilization part. So that's how we can control the overall degradation and be able to process it successfully, sterilize it, as well as store it for certain time, so that it can be used successfully in patients. So that's what we saw in this particular lecture, that we have polymeric degradable polymers for which the erosion or the bioerosion can be controlled which is basically being governed by the overall chemical affinity or the backbone structure. It is also governed by the hydrophobicity of the material. It is again governed by, though they have the similar hydrophobicity and the similar backbone, they are governed by the overall morphology of it, which is again the crystallinity or the amorphous nature. And again the processing can also induce some sort of a dependence of how the material or the device will degrade. And apart from all these factors, so that makes it much more controllable, that if we can engineer all these aspects, we can somehow technologically control the degradation of the polymer, and followed by it the processing also should be very well controlled to basically control the overall temperature and the moisture uptake of the material. So processing has to be done in a very controlled atmosphere with a very limited humidity or very controlled humidity. And apart from that, we need to sterilize the overall device so that can be used successfully, and as well be stored under refrigeration, so that if the device has to be kept for certain idle time, that can be used after certain duration. So basically with this I end my lecture here. Thanks a lot.